Hi everyone, I hope you're doing well today. This video goes over the mechanisms used by pH electrodes to sense pH in solutions. We'll start by covering the similarities to a simple voltmeter to give an idea of what's going on in the system. Next, we'll go over some basics of electrochemistry, then we'll cover how those play a role in pH measurement. Finally, we'll look at the initial design of pH electrodes and how it's been improved over the years. Let's get into it.
Just as a voltmeter measures the difference in energy potential between 2 points in a circuit, a pH electrode measures the difference in energy potential between two solutions. Visually, the two systems may look quite different, but in their simplest form, they are both just two wire leads contacting different points or solutions. First, let's look at how a voltmeter works. When measuring the voltage of a battery, a lead is placed on the positive and negative ends to form a circuit. This allows a small number of electrons to flow from the point of higher potential energy to the point of lower potential energy, which creates a magnetic field that moves the needle of an analog voltmeter.
The magnetic field strength is proportional to the voltage. Voltmeters simply measure the voltage difference that is already present in a charged battery. In contrast, two solutions do not normally have a potential energy built up between them, so a pH electrode must effectively charge the solutions. This is why a pH electrode is not just made of two wires that get placed into a solution. To understand how pH electrodes work, we first must go over some basics of electrochemical reactions.
If you are already familiar with this subject, then please skip ahead to example 2 in the video using the navigation bar below.
Here is an example of a setup for electrochemical reactions, showing two containers with two different solutions and metals inside. Each side is referred to as a half cell, and will be distinguished as either the left or right half cell for the remainder of this example. Each half cell holds a piece of metal submerged in a solution with a wire running from one piece of metal to the other. A salt bridge containing cations and anions connects the solution in each half cell. More on that later. In this particular system, one container has a silver plate submerged in a saturated potassium chloride solution. The other container has a platinum plate submerged in a solution containing dissolved iron with a 3+ charge. When electrons are present, the iron accepts an electron, or is reduced, to form an iron 2+ ion. Once all available electrons are accepted, then the reaction stops. When the wire and salt bridge connect the half cells together, the right half cell is provided with an additional source of electrons from an oxidation reaction that occurs in the left half cell. The two reactions are called half-cell reactions and can be put together to show the full cell reaction. Since the standard cell potential, also known as E0 cell, is positive, then the reaction is favorable and occurs spontaneously under standard conditions. Standard conditions are 1 molar concentrations of each aqueous solution with the system as a whole at 25 degrees Celsius.
When first set up, the pictured system does not have any iron 2+, and the potassium chloride solution is saturated, so conditions are non-standard.
Under non-standard conditions, the concentration of reactants and products determines the cell potential, and therefore how favorable the reaction is. This is defined mathematically by the simplified Nernst Equation, which states the non-standard cell potential is equivalent to the standard cell potential minus 0.0592 volts divided by N, or the number of electrons transferred, which is then multiplied by log of Q. Only one electron is transferred in the full reaction, so N equals 1. But what in the world is Q? Q is the quotient of the concentration of products over reactants. Essentially, a larger ratio of reactants to products leads to a lower Q value and higher cell potential, which makes the reaction more favorable. A larger ratio of products to reactants, on the other hand, gives a higher Q value and makes the reaction less favorable. Now, how does this explain what is occurring in our setup?
If the system has just been made, then there should not be any product, so there's a low Q and high cell potential. Iron 2+ ions spontaneously start to form by pulling electrons from the platinum plate. This results in a deficit of electrons on the platinum, which causes electron transfer from the other half cell that can be read by the voltmeter. The transferred electrons are replaced by the oxidation reaction in the left half cell, while silver chloride is formed as a byproduct. When the chloride ion precipitates to form silver chloride, then the solution is no longer saturated. This allows some of the solid KCl to dissolve and resaturate the solution. So, the chloride ions are precipitating out, but what's happening to potassium ions? While potassium is not directly involved in the reaction, an excess of cations in the left half cell would prevent additional potassium chloride from dissolving, eventually causing the reaction to stop. To prevent this, the salt bridge gives up some of its anions in exchange for potassium. In the right half cell, the opposite occurs as the salt bridge gives up cations in exchange for iron 2+. This is how the salt bridge maintains charge balance, thereby allowing the reaction to continue until an excess of products eventually makes the reaction unfavorable. The previous example provides an understanding of how and why ions flow between half cells. Now, let's modify the system to more closely resemble a pH electrode. To do that, we simply make the left side the same as the right side.
The new half cell equations are shown here. As half cells are the same, there's no electrode potential between them. Instead, the reactions provide a means of one side accepting or giving electrons to the other when acidity differs between them. More on that later. One other modification to the system is using a silica salt bridge. When this bridge is placed in solution, a thin layer becomes hydrated and exposed oxygen in the bridge binds hydrogen in solution. More hydrogen ions bind when the salt bridge is in an acidic solution. Therefore, an ion gradient develops inside the bridge when acidity differs at either end. Sodium present in the bridge is repelled from the area of higher concentration of positive charge to the area of lower concentration. The movement of sodium leads to an imbalance of charge between the two half cells. As with the previous example, this imbalance leads to movement of the opposite charge to balance the system. As the salt bridge only allows for movement of sodium ions, negative ions, electrons in this example, must move through the wires connecting the two half cells. Electron movement allows for measurement of the voltage, which is proportional to the acidity difference between each half cell. This measurement is then output by the pH sensor. So, that's the basic premise of how pH electrodes build up and measure the voltage potential between two solutions. Please note that the high resistance of roughly 50 to 500 megaohms of the salt bridge means that only a small amount of electrons end up flowing through. As such, the half cell reactions occur slowly, which preserves the life of a pH electrode. In addition, this resistance prevents depletion of the sodium ions inside the salt bridge. The following diagram compares the structure of this example system with that of a pH electrode. Electrode 1 is like the left half cell, in that it also has a wire of silver coated in silver chloride and surrounded by a saturated potassium chloride solution. A bulb made of a hydrogen selective salt bridge provides a connection to the outer solution. The main difference is that the inner solution has a 7 pH buffer added for a stable half cell potential. Please note that the exact inner solutions do vary by manufacturer. Electrode 2 is most comparable to the right half cell. Both have silver-silver chloride submerged in saturated KCl solution, aka the reference electrolyte. The difference is that the reference electrolyte in the electrode is only exposed to the acidic sample solution by a small junction, instead of actually being mixed in. An ideal junction allows the reference solution and sample to contact and complete the circuit without allowing these solutions to mix. Unfortunately, all real junctions do allow some mixing to solutions, so dilution eventually occurs. Based on the Nernst equation, a diluted potassium chloride solution results in a different Q value, thereby affecting the cell potential of the electrode. Whenever the cell potential changes, an electrode becomes inaccurate and must be recalibrated, which is why junctions are the weak point of most electrodes. Modern electrodes use various techniques to reduce the dilution problems associated with junctions. Different materials such as wood, ceramic, or Teflon may be used to plug the junction and reduce the flow-through rate. Other methods involve adding a gel to the reference solution to reduce flow. The most effective design sequesters the silver-silver chloride reference wire in a second chamber connected to the first through another junction. This is aptly referred to as a double junction electrode. All double junction electrodes also employ a plug for each junction to further reduce dilution rate. Most modern electrodes are also combination electrodes, meaning they do not have the separate electrodes that are shown in the previous examples. Instead, multiple compartments in one cylinder are used to maintain separation of the electrode solutions, as shown here. To summarize, pH electrodes rely on a combination of electrochemical reactions and an ion-selective salt bridge to produce a measurable voltage potential between solutions. While stability remains an issue due to the junction, modern advancements commonly allow electrodes to function for years without requiring replacement. Newer designs, called differential electrodes, remove the junction and prevent dilution entirely, but that's for another video. For any questions or comments, please leave them in the comment section below or contact us at contact@bionics.com. Thank you so much for watching, and I hope you have a great rest of your day.